the PE guy here. In this video we're going to be looking at single-phase circuit analysis. So the first thing about single-phase circuit analysis is that it's a very important concept. I mean, it's also a very basic concept, but you're going to need it for not only single-phase problems, but oftentimes you take a three-phase problem and you would try to convert it to a single-phase problem to solve it. In addition, a lot of problems that use the per unit system, you're going to also want to convert it into a single-phase problem and solve it that way. That's usually the quickest and easiest way to solve a problem. So the first thing to recognize is that you're going to have to take your problem, however it's given to you, and convert it into a single-phase circuit diagram. Sometimes the problem is going to be given to you just as text, so there won't be any diagrams to go by, but sometimes you'll get a diagram and then you're going to need to convert that diagram into a circuit. So just as an example, we'll look at a quick diagram. So you have a generator and it's connected to a transformer, and then that transformer is connected to some transmission line, and it has some impedance, and then the transmission line is connected to a step-down transformer, and it's connected to some load. Call that load L. And the other thing is that for the generator, they're going to give you some impedance. They're going to give you an impedance for this transformer. They're going to give you an impedance for this transformer. So now you have this system. You need to make a circuit that you can solve. Well, how do you do this? Well, you basically figure out all the impedances you have and how do they connect together. And you also got to be mindful of the sources that you have. So in this case, we have one source. We have one source, and this is, we'll just call it V. And then this source has some impedance, so we'll call that ZG. And the next thing we're going to have is we're going to have this ZT1, and then we're going to have this ZTL, and then we're going to have ZT2, and then we're going to have our load ZL. So one thing to note is that sometimes you're not these impedances might not be Z's, they might just be an X. So the transformer and the generator, they might just tell you this is a purely complex. I just wrote Z for simplicity's sake. The other thing to note is that these values might be given in ohms sometimes, but oftentimes you're going to get them as per unit values, and then you're going to have to convert everything to the same per unit base before you put it in. Before you put it in your circuit diagram. You might get a mix and match. You might get your generators and transformers in per unit. Your transmission line might be in ohms, or it might be in ohms per foot, and your load might just be, it's this many megawatts at this power factor. So you're going to need to convert everything into the same base or system, so that it can all go in one diagram. And when we get to the per unit system, you'll see how you do that in per unit, because that's where you'll see a lot of these problems will be in per unit. Okay, so now you have your circuit diagram, and this is what we're going to go into how to solve. So the first thing we're going to look at is how do you simplify this, or how do you combine these terms? So what you might want to know is what's the I of the generator. This is one thing that you might get asked. Well, the easiest way to do this is to take this circuit and make it into something a little bit more simple, and that simplified circuit is going to look like this. So you're going to take all of these different impedances and you're going to turn it into one equivalent impedance. And this one is pretty simple. It's in series, so we're just going to basically add everything together. So in this case, Z equivalent is going to be equal to, I'm just going to write Z1 plus Z2 plus Z3 plus whatever else is going to go. So now you got Z equivalent. So now you know what your impedance is. If you want to know what's the I, what current is flowing here, which this would be the I of the generator, you're just going to do I is equal to V over Z equivalent. Okay, so that's how you would calculate the equivalent impedance of something. So now let's say you have something a little bit more difficult. Let's say instead of having everything in a series, you're going to have a parallel arrangement. So you got Z1, you got Z2, and you got Z3. Well, so you still want to do the same thing. You want to take this and turn it into an equivalent impedance. So what are you going to do in this case? Well, you're going to do the same sort of thing, but you're going to use a different equation. You want to use this equation, 1 over Z1 plus 1 over Z2 plus 1 over Z3. And if you had more, you just add on to it. So the important thing to note here is this 1 over Z equivalent. This is kind of an error trap. If you don't recognize that after you do this summation, you're going to have to invert it to get the Z equivalent, because really you don't really care about 1 over Z equivalent. You really just want Z equivalent, so you're going to have to be mindful of that. So that's an error trap. You just got to be careful, and when you're using your calculator, you got to put all this stuff in there, so it might be a little bit more challenging to do that. You just got to be mindful of it. So the next thing we're going to talk about is how do you do like a hybrid sort of system. So a hybrid is this. It is going to look a little bit like this. Well, let's go with blue. So a hybrid system is going to be like this. You got this, and then you might have you have a series load over there. You got a parallel load over here. You might have another series over here, and then you got a parallel load over here. So how would you solve this sort of problem? Now, where is this going to come into play? You might have a system where you got your generator, and your generator is connected to a load directly, and then there's some transmission line involved, and that transmission line connects another load or something like that. So you might see this, but how do you solve this? How do you solve this sort of problem? Well, what I would do is I would just do it in pieces. So first, I would solve this piece of I would just add these two impedances in series. So what are you going to get? You're going to get this. You're going to get your generator. You're still going to have this. You haven't figured that out yet. You're still going to have that. But now you're going to have the green piece because you did your equivalent. So now you got this. So then the next thing you're going to do is you're going to take these two impedances and you're going to combine them in parallel. So when you combine them in parallel, you're going to get this. And it looks a little bit tedious, but once you have a little bit of practice, then you're going to be able to do this very quickly. Okay, so now you got this. So what are you going to do now? You're going to combine these two using the series equation, and now you have Now you just have your generator and your one impedance, and you can calculate. And then if you want to know, if you wanted to know, say what's the current in that part of the circuit, well, you can kind of go backwards to do that, and we'll talk a little bit about that. So the next thing we're going to talk about is kind of how do you calculate voltages and currents if you have a system like this. So first we're going to go back to that series example, and we're going to see how do you calculate voltages and currents. So this is what's called a voltage divider, because you have one voltage and each of these loads is going to share that voltage. So you have, say, let's call this Z1, Z2, and Z3, and they have a corresponding V1, V2, and V3. We still have the I. So how would we find the voltage in any one of these impedances? Well, the first thing to recognize is the current that's going through each impedance is exactly the same. They all are going to have I going through them. So we can use that to figure out what's the voltage. So if we wanted to know, say, what's V1, well, that's just going to be, that's going to be V times Z1 over Z equivalent, and we know how to solve. We already know how to find Z equivalent. And then if we wanted to know what's I, this is just a side thing. Well, I is just V divided by Z equivalent. So if you wanted to know V1, you would use this equation, V times Z1 over Z equivalent, and if you wanted to know V2 or V3, it would be the same sort of thing. So, and then the key to understand here is that every one of these three impedances is going to see the exact same current. The next thing we're going to look at is what if you have a parallel arrangement like this. Now the first thing to understand here is that all of these loads are going to have the same voltage, are going to experience all the same voltage, because as you can see, this load Z1 is connected to the terminals of the generator, and there's nothing in between it and the generator. And then Z2, it's also connected to the same two terminals of the generator, and there's really nothing between it. You have Z1, but they're, again, wired in parallel, so there's really nothing between it and the generator. And then the same thing with Z3. They're all kind of connected directly to the generator. There's nothing really in between them, and that's why they all experience that same voltage. So right off the bat, you know that V is equal to V1 is equal to V2 is equal to V3. Now that's a very important thing to understand about these parallel circuits. Now the I's are going to be different, and this is a current divider. So each impedance is going to take a portion of the current, the total current, which I didn't draw, but let me draw that here now. Let's say I have this total current I sub t. So each impedance is going to take a portion of that I total. So how do we calculate the current in one of these impedances? Well, the first thing we're going to need to find out is what is that total current, and that's just going to be V divided by the equivalent equivalent impedance. So now we know what is IT, and we know how to calculate the Z equivalent because we did that earlier. So now we have IT. So now how do we calculate, say, I1? Well, I1 is just IT is just IT times Z1 over Z equivalent. So that's how you do a current divider.